This talk is titled Mitigating Cyberattack Impacts Using Lyapunov-Based Economic Model Predictive Control, and it will discuss work performed by Helen Durand, Henrique Oyama, and Matthew Wegener at Wayne State University. The focus of this talk is on cybersecurity of control systems, which is needed for maintaining expected operation of critical industrial components and infrastructures. Attacks on industrial control systems can seek to impact, for example, profitability of operation or process operational safety by manipulating the actuator behavior. Information technology solutions provide one means for seeking to address cybersecurity concerns for control systems. Other engineering strategies can also be explored, such as techniques for attack detection from data, inherently safe process designs to prevent attacks on the control system from causing safety problems even if they occur, or control designs that perhaps combine with a detection method to enable safe operation. This talk focuses on the latter type of cyberattack resilient control strategies, or those which combine with detection algorithms. The concern for controllers which gain a level of resilience from a detection mechanism is that an attacker can evade that mechanism or be stealthy. Control theory can help with developing detection methods that take advantage of controller guarantees in the sense that when there is no detection of an attack, closed-loop stability is guaranteed for at least some subsequent amount of time via the co-design of the controller and the detection mechanism. This talk focuses on co-design of control and attack detection methods for cyber attacks on nonlinear systems, with a focus on a specific control formulation known as Lyapunov-Based Economic Model Predictive Control, or LEMPC. We focus on this control design due to its strong theoretical properties even in the presence of sensor noise and plant model mismatch. We primarily focus in this talk on a state feedback LEMPC with an attack detection strategy based on comparing state predictions and measurements at each sampling time. We close by mentioning that an LEMPC that receives state estimates instead of state measurements for a process equipped with multiple and redundant state estimators may provide another concept for co-design of control laws and detection algorithms with guarantees. In general, cyber attacks can be performed to break a typical control loop at some point. In this talk, we focus on cyber attacks that break the control loop between the sensor and the controller and provide false sensor measurements to the controller. This prevents true process knowledge from being obtained by the controller. As we will see later in this talk, this cannot be handled by techniques for handling sensor measurement noise alone. In our development of cyber attack detection and control techniques, we will focus on the class of nonlinear systems shown here. This is a class of input affine nonlinear systems with state X, input U, and disturbance W, all of which are bounded. We consider that the origin is a steady state for this system and that the system is stabilizable in the sense that there exists an explicit stabilizing control law H of X that can render the origin asymptotically stable in the sense that there exists a Lyapunov function V with a negative definite time derivative along the closed-loop state trajectories without disturbances for all states in a neighborhood D of the origin. We define a level set of the Lyapunov function contained within the region where V dot is negative as the stability region, shown in the figure on the right. We consider that full state measurements are available continuously for this system, but that they are impacted by bounded measurement noise. For this class of systems, we will be exploring the impacts of cyber attacks on sensors for the feedback control law known as economic model predictive control. The general formulation of an economic model predictive controller receiving feedback of the full state is shown on this slide. It consists of a general stage cost, dynamic process model, state measurement, input rate of change constraints, and input and state constraints. The input rate of change constraints may be added to prevent the control actions computed by the EMPC from being overly aggressive. With additional constraints to be discussed subsequently, this control formulation has theoretical guarantees regarding feasibility and stability in the presence of sufficiently small bounded measurement noise and disturbances. False sensor measurements do not ensure boundedness of the error in the state measurements, and therefore do not necessarily allow these guarantees to be maintained. The additional constraints which allow the closed-loop stability guarantees just described to be obtained are Lyapunov-based stability constraints that, When added to the EMPC formulation on the prior slide, and with a slight change in the way the input rate of change constraints are enforced for feasibility reasons, give a formulation of Lyapunov-Based EMPC or LEMPC. This control formulation has two modes of operation, where the first utilizes the constraint shown in red. This constraint requires the state predictions to remain within a subset omega rho E1 of the stability region omega rho. This constraint is designed using the explicit stabilizing controller h of x, and that controller is guaranteed to meet all state and input constraints at every sampling time. This control law also allows us to guarantee that the closed-loop state is always maintained in the stability region omega rho, and also to ensure that the measurement, even though impacted by noise, is also maintained in omega rho. The second mode of operation of LEMPC allows both feasibility to be guaranteed as well as stability, in the sense that if the mode 2 constraint, shown here in blue, which enforces a decrease condition on the Lyapunov function, is enforced repeatedly, it can drive the closed-loop state to a neighborhood of the steady state. Though the control law just described has attractive stability properties, cyberattacks on state measurements provided to that controller could prevent those stability guarantees from being realized. This is because even though the guarantees just described can hold in the presence of sufficiently small sensor noise, a cyberattack may act like insufficiently small sensor noise. This indicates that it would be desirable to detect an attack by looking at the deviation of measurements from the actual state. A method of approximating the actual state is through state predictions from the last measurement. This gives one idea for a cyberattack detection strategy for LEMPC. The difference between the measurement and the prediction of the state could be checked at each sampling time. If the difference is larger than an expected threshold, the state measurement can be flagged as a possible attack. If it is below a threshold, it should be able to be tolerated by the controller for the subsequent sampling period in the sense that the closed-loop state should still be within a bounded region of operation at the end of the sampling period. Based on the fact that LEMPC with sufficiently small measurement noise can retain closed-loop stability in this sense, it should be possible to design an LEMPC that can maintain the closed-loop state in a bounded operating region after what I'll term a sufficiently small cyberattack, meaning one which does not trip the detection mechanism, occurs. In this discussion, we see the concept of controller and detection mechanism co-designed for LEMPC, in that the resilience of the controller to the cyberattacks that are not detected for at least a sampling period after the attack occurs will come from the LEMPC's design in tandem with the threshold design on the attack detection method. Here, we note benefits and limitations of the proposed method. Some of the benefits are that it offers a way of flagging attacks based on state predictions, and it allows closed-loop stability to be guaranteed for a sampling period after an attack that does not cause too large of a deviation of the falsified state from its predicted value. Because closed-loop stability is guaranteed for the subsequent sampling period, this gives some buffer time for a potentially secondary detection mechanism to attempt to detect the attack after its occurrence before the closed-loop state leaves a safe operating region. If the attack is detected by such an auxiliary detection mechanism, backup strategies can be activated to maintain safety at all times. A significant limitation of the method, however, is that it does not guarantee closed-loop stability after a single sampling period following an attack. This is because it relies on a state prediction from the value provided as the sensor measurement at the last sampling time. Once the last sensor measurement is falsified, the predictions coming from this value are no longer representative of the process state. This can be thought of like the state never receiving true feedback when an attack is occurring, and like sensor noise having a potential ability to grow over time. We will now provide an illustrative example to clarify the concept that cyberattacks resulting in falsified state measurements, if they are close to the actual values, may not cause an economic model predictive controller to show closed-loop stability issues in a sampling period, even if Lyapunov-based stability constraints are not used. We also demonstrate potential issues with continuously falsified measurements. In this example, a continuous stirred tank reactor with a second-order exothermic A to B reaction is examined. The control objective is to optimize the economics of this CSTR while maintaining safe operation. The economics-based objective function to be maximized by the EMPC is the time integral of the production rate of the desired product. Manipulated input constraints are enforced for physical reasons. 5 cyber attacks on the sensors were performed on this system at T0 by providing combinations of CA and T with the values of CA and T in the ranges noted. These falsified state measurements resulted in the inputs shown on the right, where different colors represent different scenarios, and the black trajectories are those corresponding to the unattacked case with true sensor measurements. It can be seen from the figure that the inputs computed under the various scenarios were quite close. These led to very similar state trajectories that are overlapping on the left. This indicates the principle that in the presence of a cyber attack, for which there is a small difference between the actual and falsified state measurements, the inputs computed by an EMPC may not be significantly different. This highlights as well the reasonableness of the proposed method for cyber attack detection and closed-loop stability, involving checking how significantly a state measurement and an expected value of the state coming from the prediction differ. Next, we look at how measurement noise and false sensor measurement cyber attacks can differ. Here, we provide a false state measurement to the controller at every sampling time and look at how the actual state evolves compared to the false state trajectory. The false state trajectory is obtained by simulating the process dynamic model, where at every sampling time, the initial value of the false state measurement is set to be 0.2 kilomole per meter cubed and 5 Kelvin above the predicted values. These are being predicted from the last value provided as the measurement to the EMPC, which was false. The simulations indicate that despite that at every sampling time, the falsified state measurement is within a bounded amount of the values predicted from the prior value provided to the LEMPC, there is a potential for error between the predicted and actual state to grow over time. This demonstrates the concept that measurement noise and false sensor measurement cyber attacks are not equivalent, because while with measurement noise there is some error at every sampling time, that error is within a range of the actual measurement. In contrast, in false sensor measurement cyber attacks, effectively, feedback of the process state is not obtained, perhaps not even approximately. These simulations highlight that a key limitation of the proposed method for attack detection and resilient control is that the detection technique relies on state predictions. Once one measurement is falsified, the predictions are no longer reliable. A concept for overcoming this is to replace the state feedback LEMPC with an output feedback LEMPC, meaning an LEMPC that utilizes an estimate from a state estimator in its design. If redundant state estimators are available and only the one used to provide estimates to the LEMPC is impacted by a sensor measurement attack, the others can be utilized to flag this because, in effect, they provide a check on whether the state estimate being received by the LEMPC is sufficiently accurate. In conclusion, detection mechanisms using LEMPC may take advantage of control theoretic guarantees in detecting attacks. In this work, we focused on a state feedback LEMPC formulation that was considered to mitigate cyber attacks in the sense that it guarantees closed-loop stability over a sampling period in the presence of disturbances, measurement noise, and false sensor measurements within a bound on the error between the prediction of the state from the last measurement provided to the LEMPC and the state measurement at a given time. When the attack is not sufficiently large to be detected at a sampling time, then if an auxiliary detection mechanism does not detect it during the subsequent sampling period, closed-loop stability could be compromised after that time. To overcome this, other techniques could be tried, such as using an output feedback LEMPC with multiple redundant state estimators, where only the estimator providing estimates to the LEMPC is assumed to be able to be impacted by false sensor measurements. We gratefully acknowledge financial support from the National Science Foundation and Wayne State University.